Okay, then beside these formulas, right, there's another very important method that can be used to determine the characteristic of the PSK. So we call it a quadrantures method. Quadranture method is, for this is widely used at the moment because it's very straightforward. So later on, we can use some of the example to try to introduce, and it's not introduced, to revise the quadrantures method. So how it goes is, so for instance, give me an example of the M. M is a multi-level, yeah, M PSK signal of the form of this. Yeah, this is a very general mathematical expressions. So you can represent by the superposition of cosines and sinusoids, right? Cosine and sinusoid. So when you implement in the practice, you can see this is the whole circuit is going to be used. So I will not spend too much time here. Yeah. So getting the cosines, omega CT and sines omega CT adding together become a channels, right? So you can see later on in the last lecture, in the last question in the tutorial, something is going to be used, something like that. Okay, so for that quadrantures method, we use the constellations diagram here to give in a very visual illustration. Oh, yes, please.
I would like to ask, what the position of sine and cosine?
Ah, okay. So, sorry about that. So it's just this one, this formula here. You can use some trigonal mathematical expression to break this one into cosine plus a sines. Yep. So actually, you get cosine something plus a sine something is equal to cosine. There's a quarter x plus y, something like that.
Yes.
So if you, seems like the network is not great, isn't it? Totally don't understand. Yeah. How's now? Is it good now? Okay. So because this is difficult, right? So if you still have these questions, I think when we go through the last question in the tutorial, then you will have a better understanding. So remember, this chapter is a bit difficult. This involves lots of calculations. Yeah. So for better explanation of the superpositions, we can go back to the last question in the tutorial. Then you can have a better understanding. Yep. So don't worry about guys. I will try to guide you through. Okay, so let's go again. So constellation diagram is very important. So if you don't understand the superpositions, yeah, because I think we prepare you don't fully understand the superposition. But lucky we have the constellations diagrams to try to solve the problem. Yeah, actually speaking, you don't need to care about the superposition of cosines or sines, whatever. For me, it's not worth to spend that much time to try to understand the superpositions. What you try to understand is the constellation diagrams. It's much more useful because it gives you the visual impact, a visual understanding on the modulation's behavior. Yep. Okay. So actually speaking, for the last question in the tutorial, right? If you went through it, I think I will, even though Katrina have a solutions that using the superpositions, yeah. But for me, I will use the constellations diagram to try to solve it. So later on, you can see how I'm gonna solve it. Yeah. Okay. So how does this constellation diagrams look like? So from the definition is the in phase versus the quadrantures maps. Yeah, getting a two-dimensional diagram. So you can see from this diagram the magnitudes, yeah, of the in phase, which is called cosines, and the quadrature, which is called the sines, can be determined. Yeah. And then for the for instance the MPSK, so you can distribute it in a circular pattern. It looks like it's quite complicated, yeah, for the description. But let's look at the graph. It's better, isn't it? Yeah. So this is the graph. So you can see this is the constellation diagram. So I'm pretty sure that you guys know it already. Yeah. So the initial phase. So for the PSK, yeah, for the initial phase for PSK is always equal to time divided by m. Yeah. So for instance, m BPSK, m is equal to 2. So the initial phase is pi over 2. Yeah. And then for the QPSK, yeah, the QPSK, the initial phase is pi over 4. Yeah. So you can see straight away, you see from here. So this is the pi over 4 here. Yeah. This is pi over 4. So this is a degree. Yeah. You can see I draw a line here. Yeah. So for instance, 0, 0, you get in line to the original point here. This is the magnitude. And this is the angle, right? Which is the initial phase. So for QPSK, the initial phase is pi over 4. So this angle is equal to pi over 4. So if you're using a superpositions, you try to understand this one using a superposition angle, it's okay as well. You know, you can see this one, you can see this one here, and this one here. Yeah, you get in the vertical axis and the you get in the horizontal axis here. So the in phase, it stands for cosine functions, and the quadrature is stand for the sine functions. Yeah, it's kind of complicated, right? But actually, it's not. So we can go to some straightforward, you know, explanation in the constellations diagram. But let's move away here. So for APSK, the initial phase is pi over 8. So that means if you draw a line for 0, 0, 0, yeah, if you draw a line from here to here, right? So the angle in between here is pi over 8. Yeah. So if you go to 0, 0, 1, right? So what's the next phase? You can add something into it. So for instance, 0, 0, 1, you draw a line to here, and the angle between here is pi over 8, and plus the angle between here and here. So it's something like that. It's not so difficult, but the calculation is a bit complicated. So I think lots of students experience a lot of difficult when solving the question 3, in my opinion. Yeah, in my opinion. Then this is much more complicated. Yeah. Then you go to a quadrature amplitude modulation, which is called a QAM. It's much more difficult than the ASK or PSK. It's combinations. So you can see just now for the PSK, you can see 0, 0 to the original point. For instance, a QPSK, yeah? 0, 0 to the original point, 0, 1 to the original point, 1, 1 to the original point, and 1, 0 to the original point. They all share the same distance. So the amplitude does not change at all. The same as the APSK, you can see order is just a circle, yeah? So the radius for the circle, or sorry, for the diameter of the circle is the same. So that means 0, 0, 1 to the original point, or 1, 1, 0 to the original point, they all have the same distance. So they not modulate with the amplitude. For QAM, it's a mixture of ASK and PSK. So you modulate the phase, also you modulate the amplitudes. So that makes it something is very difficult. But the thing is, the more complicated it is it's much more widely used nowadays, unfortunately. Yeah, it's used in computer modems, mobile communications. You know, there's lots of digital television, yeah, and audio broadcasting. So how does it look like? Let's go to here. Yeah, this is much better, isn't it? So you can say for PSK, yeah, 16 PSK. So you're getting 16 dots within the whole diagram. So you can see it's a circle, isn't it? So each point, yeah, each point to the original point, they all share the same distance because it's a circle. But the thing is, for the QAM, 16 QAM, you also have the 16 dots, yeah, into the constellation diagram. But you can see 110 from 110 to the original point and 000 to the original point, they all have a different distance. So that's why the QAM is a combination of the ASK and PSK together. So I'm pretty sure that you know, possibly people try to distinguish the student from a high distinction, right, to the past. They might get in some understanding, understanding of a QAM like that to try to, you know, make the student experience difficulty in the exam, right? Isn't it? Okay. So this So this is how we like. Okay, so let's go to our questions here. Yeah, let's go to a question here. So this exam question 3A here is getting a two constellation diagrams. Yeah, so you can see this one. Yeah, you getting this one and this one. So this one, how many level gonna be? Yeah, we can straight know it's a QAM. Yeah, because you can see from the center point here, the point, this dot to the point here, and from this dot to the point here is different distance. So that means this is a QAM. Yeah, it's a QAM technologies. But how many level gonna be? So how many level? That means you just calculate how many dots. You get 1, 2, 3, 4. So 16 dots. Yeah. So this is a 16 QAM. And then you're getting one here. Yeah. You can see from here to here, from here to here, from here to here, from here to here is a constant distance. So you can see this is a PSK. You can say this is a PSK technologies, right? You have how many levels? So you're getting 1, 2, 3, 4 dots. So you can see this is a 4 PSK. Yeah, 4 PSK. Yeah. But there's another possibility as well. You know, it also can be a QAM. But when QAM equal to 4, yeah, only 4 dots, you can see this 4 dot only. They all also equal to each other. So you can call this is a 4 QAM or 4 PSK. Yeah. So it's easy. But now we're gonna ask you about a 32 megabit per second binary encoded data stream is modulated using these modulation formats. So what is a 33 megabit per second? So this is the definitely, yeah. This is a baseband. Yeah, it's a baseband bit rates. So what is the bandwidth of the signal in both cases? So they assume an NRZ line code. So now we have to use lots of formula that we talked about it a few slides ago, right? So now, remember this is the NRZ line code. It's a polar NRZ line code, yeah? So I think this question is, you have to add a polar NRZ line code to make it much more clear, isn't it? But normally speaking, as I mentioned in the table, last lectures, yeah? So for all the NRZ line coding scheme, so the first root bandwidth should be equal to the bit rate. But for the RZ scheme, so for instance, return to 0 or Manchester coding, yeah, so it should equal to 2 times of the bit rate. Yeah, remember I summarized it in the tables. So here, even though you not talk about polar, yeah, polar NRZ, but straight away we know, yeah. So for NRZ line coding, the first root bandwidth should be equal to the bit rate. So it's something like that here. But don't forget this is a baseband, yeah, baseband. Then when we go to the modulations, yeah, so it's equal something like that. Remember this formula that I emphasize you guys to pay special attentions. So it's equal to 2 times the B, yeah, B, remember, baseband bandwidth, which is equal to 33 megahertz, and divide by log 2 M. So M is the level, yeah. So for instance, 16 QAM, M is equal to 16, yeah, and 4 QAM or 4 PSK, yeah. So the M is equal to 4. So you know the M, you know the B, straight away you know about bandwidth, yeah, for the modulations. So it's testing the understanding of the concept, the difference definition between baseband bandwidth and the modulations bandwidth. Okay, so now for next one, we're gonna talk about the decision regions. So before that, I would ask students if you have any question regarding on this slides, you can send me a message now, or you can talk to me. If not, I can quickly move on, and then we focus a lot attention in the tutorial questions, maybe. Yeah. Repeat again. Okay, which part you want to repeat? Still them. You want to repeat the questions? Seems like these two formula. Okay, great. Okay. Yep, good. Okay, so let's go to these formulas. Yeah. Okay, so actually, I might can open the previous slide, right? Okay, so now you can see it, right? So this is the previous slide that we talked about it. So you can see for NRZ, yeah, none return to zero. None return to zero, yeah, polar NRZ, unipolar NRZ. So you can see no matter is polar or unipolar, the first new bandwidth is always equal to the bit rates, yeah, for the baseband signals. Yeah. For the RZ here, return to zero, is always equal to 2 times of the bit rates. So this is the major difference. This is also is a trend for understanding. Yeah? So back to the question here. So you can see here is assuming the NRZ like code. Yeah, isn't it? So a 32 megabit per second encoding is binary sequence encoding is a bit rate. Yeah, it's a bit rate. Then the question we're gonna ask you, here is what is the baseband bandwidth first when you're using the NRZ like code? So don't worry about the polar or unipolar. Who cares about this one? We don't care about the NRZ. Yeah. So according to the table that I showed you guys just now, so the bandwidth, the transmission bandwidth of the NRZ like coding is equal to the bit rates, yeah, which is equal to 32 megahertz. Then for this formula here, this formula, remember? Yeah, this formula is here, yeah. So for the bandwidth of the moderate, for the moderate signal transmission, it's not baseband, yeah, it's moderate signals. It's equal to 2 times of the BT, which is the bandwidth, yeah, which is the first node bandwidth of the baseband signals, yeah, under the line coding scheme. And M here is how many level of the modulations. So it's the same here is here, right? Because we know about the baseband bandwidth, yeah, the first node bandwidth, which is a baseband bandwidth, is a 32 megahertz. So B is equal to 32 megahertz, and M here is depend on the modulation technologies, yeah. So for instance, 16 QAM, M is equal to 16, or 4 QAM or QPSK, Q is means 4, yeah, quarter. So it's 4. So M is 4, yeah. So you can see this formula like that here. So it's not difficult, but it's just testing your understanding. That's all. So let's see. 4 point can clearly separate to, oh yeah, that's right. So 4 point, the for QAM and for PSK is the same. So will exam paper provide the formula? Look, I'm not quite sure, because this is not a formula, it's a characteristic, isn't it? But this formula, I think it should provide it. But for the line coding scheme, for that, the first node bandwidth equal to bit rate or 2 times of bit rate, I'm not sure it's gonna show in the exam paper or not. But for this formula, I think for me it should be shown because it's a very important formula, right? Okay, so let's move next to the decision regions. Okay, so so later on, it's just the comparisons, right? So you get in a constellation diagram, you get in different bit the region for different for different symbols, yeah. So it just, for instance, you get in a the message is somewhere here, yeah. So you have to look for the close the minimum distance. Yeah. So for instance, here, within the region, so it should belong to 0, 0, 1. Yeah. So here, in here, it should belong to 0, 1, 0, and here should belong to 1, 0, 1. Yeah. So it's not so difficult. But thing is, for instance, if you go to a boundary here, it might be difficult to distinguish between 0, 0, 1 and 0, 0, 0. So you can either go to 0, 0 or 0, 0, 1 in this regard. But for this one, you can see, or still, you can see distance from here to here, and here to here is, this one is much more closer and it falls within the region, isn't it? So you still can say this is 0, 0, 0 in this regard. But in some cases, right? So for instance, this is the 8 QAM, yeah. But how about you getting 64 QAM? So that means your the size is more double, isn't it? So in that case, the smaller the region it is, the easier you're getting interrupted by noise. So this is how it goes. So even though the more level it go for modulations, you're getting much higher bit rates, isn't it? But the thing is, you can also easily interference by the noise because your regions within the constellation diagram is much more smaller. So sometimes you get the noise, for instance, you get the noise to shift just a little bit here, then the system is difficult to distinguish between it's a 001 or 000, for instance. So you're getting a wrong information. So this is a trade-off. So this is what I mean just now, yeah. So it's very similar to the baseband communication where we use for Shannon's channel capacity formula, yeah, to determine practically how many bits can be used to encode data. So for the Shannon's channel capacity formula, you can go back to the lecture slide or go to the textbook to try to have a good understanding, because it is to determine, the minimum bit to attain a signal to noise ratio, a certified signal to noise ratio. Okay, so you can see, yeah, this is regions. So for instance, you're getting a BPSK or 2 QAM, you can see something is in between. Yeah, it's the distance. Yeah, the distance here should be, should be almost equal, isn't it? Yeah, the same as the QPSK, the decision region. You can see you're getting a line here. So this point to this point, the decision region, the boundary should be divided equally, and from here to here, the boundary should be divided equally as well. So I'm pretty sure it won't cause any misunderstanding for you guys, because it's very straightforward and it's a visually understandable. Okay, so now we go to exam question 3B here. So it also testing your understanding of the constellation diagram and try to make students thinking about the decision regions. So straight away, you're getting a BPSK, yeah, a BPSK here, yeah, and OOK, which is the on and off keyring, which stands for the binary, yeah, 2 level only for the ASK. So it asks you what is the decision regions, yeah, for the diagram. Simple, isn't it? So you just straight away, getting to the distance here, and then clock it, getting a line in between, the distance here, getting a line in between, and that's it. That's the decision regions. But now the second question is explain why the SNR, so it's a signal noise ratio, yeah, for OOK needs to be twice the SNR of the BPSK to achieve the same probability of error. So this is really depending on the decision regions. So how it looks like, let's go to the solution to try to understand it. So you can see the distance, yeah, between here to here. You can see the boundary. You're getting this is 1 square, 2 square, yeah. So each point you have 2 square to the boundary. But for the OOK, yeah, this is 2 PSK. Or BPSK, yeah, it's 2 PSK. So for the OOK, which is 2 ASK, you can see the dot to the boundary is only 1 square, yeah. So that's why you can see this is the explanations, yeah. You can see that in the the BPSK case, the distance between two symbol is double the distance. So you're getting 2 square here, and here is only 1 square. So that means the average power of the moderate signal for the OOK is half compared with the BPSK. So that's why we did double the SNR to achieve comparable performance. So when this question is asked, it's really connected to the decisions, regions, right? So the larger distance to the boundary, the better SNR gonna be. So this is the trend. And for this one, I recommend you, if you try very hard to understand but could not, maybe just try to memorize it. Yeah, to try to get in a better explanation when it's gonna ask in the exams. I'm not sure it's gonna be in the exam. It seems like this is a short answer question, isn't it? Okay, so finally, so this is all, but you can see in the sample exam question, it's not that difficult, right? But in the tutorial, it seems like it's complicated, isn't it? So what I'm gonna do is I'm gonna go through the tutorial questions with you guys, and then you guys will spend 45 minutes, so you get 3 questions, right? So 15 minutes each questions. Then after that, after 45 minutes, I'm gonna go through the answers with you guys. So now it's the tutorial questions here. So I think you guys can open the tutorial questions, or you can look at the screen as well. It's up to you guys. Okay, so you can see it's only 3 questions, yeah, because the final question is a bit difficult. The first question is asking about the bandwidth of the OOK and FSKs. Yeah. So let's read through the questions to try to understand. So in the question is asked about a binary baseband signal is passed through a rise cosine filter. So it's not square wave anymore. It's a rise cosine filter. So for the bandwidth, you need to add the rollover factor in. Yeah. So luckily, the rollover factor already know is 0.5. Yeah. And it's then modulate onto a carrier. So data rate, yeah, data rate is bit rate, right? Isn't it? So data rate here is 64 kilobits per second. Then the question will ask you the absolute bandwidth of the resulting OOK signals. Yeah, lucky we have the formula, right? Isn't it? The second question is the approximate bandwidth of resulting FSK signals. It say where a 0 is modulated onto a 150 kilohertz carrier, and a 1 is modulated onto a 150 kilohertz carrier. So I think to try to answer this question, you can go back to the PowerPoint slide, right? In the example slide, right? So please look at from here, from here, yeah, here. Oops, not PPSK. Yeah, from here, this slide, maybe you try to understand it, yeah? I trust you guys can know about this slide very well, right? So you can use some of the formula from this slide to try to solve the problem. Okay, so for the second question, is also asking about the bandwidth, but this is for PSK. So looks like the bandwidth is very important compositions into the exams for this workshop, yeah? So bandwidth. So what it say is, assuming a baseband PCM signal is produced at a data rate of RB equal to 9600 bits per second. So this is a bit rate, yeah, isn't it? And another thing is, another hint provided by this question is, it's encoded using a rectangular polar NRZ pulse. So you can see, okay, I know the bit rate, then I will know the first node bandwidth of the polar NRZ light coding scheme, isn't it? Which is the baseband bandwidth. And then once you know that, you're going to talk about PPSK, QPSK, and 64 PSK, isn't it? Yeah. So the question, I think the formula is here, right? The formula is straight away, simple. Yeah. So remember this formula? Yeah. I think it should be easy. So it seems like the first two questions is very easy, and you guys need to just spend like a few minutes to try to answer it. But for the final question, it's a bit difficult. So it gives you a different keying techniques here already. Yeah, so you have to have the sequencing for 1011 01001011010. Yeah, seems like it's difficult. And if this sequencing is modulated using a QPSK technology, yeah, and then what is the carrier phase if you choose? So this is the questions. So that means you have to know about what is the modulated signal express mathematical expressions. So you know about the amplitude and the phase. This is something difficult, isn't it? But the thing is, for the QPSK, you can break it, yeah, because every time you modulate it two bits, yeah. So you can break it, 1011 01 00 1010, yeah. The second one you use the APSK. So APSK, yeah, you're getting 3 bits each time, yeah. And lucky, yeah, this guy already told you it's a pi over 8 for the initial phase. So it's good. So that means for the APSK modulation techniques, you can modulate 101 for the first modulation, 101 for the second modulation, 001 for third modulation, and 010 for the fourth modulations. Then you're getting a 16 QAM. Wow, this is the most difficult one, isn't it? 16 QAM. So 16 QAM, that means you're getting 4 bits, yeah, 4. So each time you modulate 4, yeah, 110, yeah, something like that. So that means for this data sequencing, you can modulate, the first modulation is 1011, the second modulation is 0100, and third modulation is 1010. So you can see as you increase the level of encoding, it's much more efficient to transmit, because you can see for the 16 PSK, you can transmit 3 times, that's it. For the QPSK, you need to transmit 8 times. Okay, so 45 minutes. So I would like you guys to spend 45 minutes to try to attempt the questions. Yeah. So later on, I prepare, you guys will ask a lot of things for this tutorial, right? So try to attempt it. Then later on, when you explain it, it can be much more easy to understand. So now I will see you guys in 45 minutes. That means it's 11:45 p.m. in Melbourne. So it's 8:45, yeah, 8:45 in Hong Kong. Yep. So I will see you guys 8:45. All right. So I'm gonna disable the audio and video, and good luck, guys, and please try to attempt the questions. Then later on, you're gonna be more efficient. Hello guys. So I hope you guys all back to the chat room. So is my voice okay? Yeah, the pictures are fine. Okay, good. That's good. Yeah, hopefully it's fine, isn't it? Okay. So now I will do a share screen on the PDF file. Okay, voice okay, but delay occur. Okay. Yeah, it seems like the speed is yeah, so isn't it? Yeah, it's okay. Yeah. Okay. So now let's go to the solutions. So just now we went through the questions. Now we go through the answers. So there's 3 questions in the tutorial. The first and second, you can see when we went through it like back in 1 hour ago. Looks like it's quite simple, isn't it? It's just to substitute with the formulas, choose the right formula, and that's all. It's just the final one is getting a bit complicated because there's lots of trigonometric mathematics calculation gonna be involved. So let's go to the first questions. So I repeat the question again. So you can see is there's a right cosine filters with a row of factor of 0.5. So that means it's not the square wave is a right cosine wave. And then the data rate is a 64 kilobits per second. So that means the RB is a 64 kilobits. So now it's asking about the absolute bandwidth of the resulting OOK signals. Yeah. So as we mentioned just now in the lecture slides, so for the FSK, you can see there's a lot of things involving, yeah, with the Carson rules things. But actually, for the ASK and PSK, you should go to very simple one. It just because it does not involve with the frequency, so the Carson rule does not apply anymore. So which means the bandwidth of the effective bandwidth or the ASK or the PSK, the BPSK, for the ASK is the OOK is a binary ASK, yeah, OOK. For the BPSK, for the square wave shapes of the signals, right? So the bandwidth is almost equal to 2 times of the bit rate, as shown here. If the right cosine shape pulse is involved, so that means we have to get the 1 plus the root over factor times the bit rate, because we don't involve with any modulations that seems like the FSK cases. So that's why you can see we can just use the formula straight away. So W is the effective bandwidth for the ASK, for the OOK, sorry about that. For the OOK is equal to 1 plus R. R is 0.5 and RB is 64 kilobits per second. Then you just do the calculations. So 1 plus 0.5 is 1.5 times 64 kilo per second is equal 96 kilohertz. Yeah, it's simple, isn't it? Then for the FSK, the effective bandwidth, right? So let's go to the formula again. So this is for FSK, yeah. So now you have the bandwidth is equal to because we use a right cosine shapes pulse, isn't it? So the effective bandwidth is gonna approximately equal to 2 times of the delta F max, which is the frequency durations, plus 1 plus R get a quota times the bit rate. So we know the bit rate is 96 kilohertz. The R is 0.5. The only difference we don't know, the only known factor we have is the delta F max, which stands for the frequency durations. So what kind of information does it show to calculate the frequency durations? So from the definition of the frequency durations, that means is the difference, the max difference between the carrier frequencies, yeah, and also the frequency for the zero modulations and the one modulations. Okay, let's see that. So for the zero modulated frequency, it's 155 kilohertz. And then for the one, which is the peak of one for modulated, is at a 150 kilohertz carrier, right? So that's why the difference, absolute difference is 155 minus 150 is equal to 5 kilohertz. But don't forget, this is the swing up and down, right? Situations for the peak 1 and 0. So for the maximum frequency duration, it's equal to 5 kilohertz divided by 2, which is equal to 2.5 kilohertz. So that's why the delta F max is come from is 2.5 kilohertz. So now we know the delta F max and also the R. We know the RB. So now we can know is 2 times 2.5 kilohertz is 5,000 plus 1 plus R times RB, which is 96,000, which is substitute from here to here. And then finally, you just add it simply together, it's become 101 kilohertz. So you can see the it's not difficult at all. So let's see what question it is. Okay, so okay, rise cosine. Yep. Okay, so the part that the A part again. Why no need to divide by 2? Okay, so this is according to the formulas here. Yeah. So for the OOK, which is a binary ASK, and for the BPSK, right? So this is the formula that show in the lecture slides. Yep. So this is for square shapes. Square shapes is the effective bandwidth is almost equal to 2 times of the bit rate. But this time we have a rise cosine filter here. Yep. So that means the effective bandwidth is become 1 plus R. R is a roll-over factor times the bit rate, RB. So this is where we put this formula into the calculations here. Yeah, into the calculations here. So it makes sense? Nope. Looks like yeah, ASK, LOK is the same when using the rise cosines. Yeah, for BPSK. So OK is a binary ASK, yeah. Then BPSK is the binary PSK. So OK is equal to BPSK for the effective bandwidth. So this is the things, yeah. For OK is a binary ASK and BPSK is a binary PSK. So for the effective bandwidth calculation, OK is going to be similar to the BPSK. So I think in the solution, I think Katrina already explained quite well why the formula become like that. So if you, but this one definitely you have to go back to the lectures to talk about the digital modulation and the textbook to describe this one more detailedly, because this one is only come from the shorts. Yeah. Okay, so go to the second questions. So you can see the bit rate is 9600 bit per second here. Yeah, and it's a polar NRZ. So it's a rectangular polar NRZ, right? So from the table that we show in the lecture 2 for the pre-exam workshop, so the bit rate is equal to the first node bandwidth of the baseband signal. Yeah, so it's a 9600 bit, 9600 hertz. Now we know the baseband bandwidth, but now we have to calculate the bandwidth using different modulation schemes, which is a BPSK, QPSK. So BPSK, the level is 2, so it's 2 PSK. QPSK is 4 PSK, yeah, 64 PSK. So getting a 2, 4, and 64. So we go back to the formula here, right? So this is the formula that we're going to use. Yeah. So this is M stands for how many levels it's going to be used for encoding. And then for BT is actually the first loop bandwidth of the baseband signals. So which is equal to 9,600 here. Yeah. So now, okay, that's all. So for the binary PSK, yeah, binary PSK. So actually, you can just go to these formulas, yeah, these formulas. So M equal to 2, yeah, M equal to 2. So log 2 over 2 is equal to 1. So that's why it's W equal to 2 times BT here. So you just need to times 2 times 90.6 kilohertz and become 19.2 kilohertz. Yeah, that's for BPSK. For QPSK, because the level is become 4, so this become log 2 over 4 is equal to 2. Yeah, you can use the calculator to prove it anyway, isn't it? So that's why you have to bring the calculator into the exam venue to try to be more effective. And then 2B here is 19.2 kilohertz. So 19.2 kilohertz divided by 2 is equal to 9.6 kilohertz. Then for 64 PSK, yeah, that means the M is become 64. So log 2 over 64 is what? Yeah, it's gonna be 6. So log 2 over 64 is become 6. So 19.2 kilohertz divided by 6, it becomes 3.2 kilohertz. So that's why, basically speaking, we try to test you the understanding of these formulas. Yeah, these formulas here. So what you need to do, the first one is to determine what's the level for the modulation scheme. Yeah. The second one is what is the effective bandwidth, what's the bandwidth for the baseband. Yeah. So for instance, is a polar NRZ. Yeah. So how about the Manchester? Yeah. So the baseband bandwidth gonna be changed. So please be careful. But you can see lots of questions asking about the polar NRZ. Yeah. So this is okay, straightforward. You don't need to. You just the first loop bandwidth is equal to the bit rate straight away. Yeah. So make it very easy. So any question for this one? Seems to be easy, isn't it? Okay, so now we're gonna focus on the final questions. So the final question is gonna be a little bit difficult, I can see. Okay, so the final questions. So getting the scheme, yeah, sorry, the Tata sequencing is the 1011 01 00 1010. Yeah. So you can see for the QPSK, which is is 4, yeah, you're getting 4 levels, yeah, 4 dots, yeah. They're getting APSK, so getting 8 dots. Then you're getting a 16 QAM, so you're getting 16 dots, yeah. So what's the question asked is, calculate the carrier phases and amplitude of the modulated waveform for this sequencing, for the following modulation schemes and constellation diagrams. So first thing first, we should know about the expression, the mathematical expression, isn't it? So the mathematical expression is not that difficult, right? So it's shown in the from the pre-exam workshop lecture slides. Yeah, which is here. Yeah, so you get in a the carrier amplitudes, yeah, the carrier frequency, and the 2 pi m, which is levels, and then m is the position that where you're in. Okay, so now for the we know about the formula, right? So now we have to break the data sequencing. So for instance, the QPSK, because it's 2 bits each time, right? So this data sequencing becomes something like that. So become 10 11 01 00 10 and 10. Yeah, you break it into 1 2 3 4 5 6 parts. Then you can see Then you can see 1, 0, yeah? 1, 0. You're getting 1, 1. 0, 1. And 0, 0. And 1, 0 and 1, 0 is the same as the first one. So you just need to solve the 1, 0, 1, 1, 0, 1, and 0, 0. And that's all. Yeah. So let's go to 0, 0 first. Let's go from the backward. Yeah. We go for 0, 0, which is the simplest. So I screenshot something like that here. Yeah. Okay, so for 0, 0, so what you're gonna need is you get in a what's the magnitude? Yeah, we have to know about the magnitude here, and also we need to know about the angle. What's the angle? Yeah, what's the angle here? That's very important. So for the magnitude here, yeah, if you get in a rectangular, yeah, get in a triangle. My writing is not very good. So you can see the magnitude for this line here is 1. Yeah, it's 1. Yeah, and then for the magnitude from here to here is 1. So what is gonna be? Yeah, isn't it? So this is so you can just solve this one without any problem here, right? So that's why it's become let me type something here. So this is become let me just write. So this one is become 1 square, okay, plus, my mouse is not great, 1 square. So that's become 2. Yeah, so this has become square 2. So that's why you can see this is where square 2 come from. This is amplitudes. Then the second difficult part is I need to know about the angle here. Yeah, what's the angle? Yeah, the theta. What's the theta? Yeah. So as you know, the initial phase, yeah, the initial phase, if you look at the formulas here, let me check where's the formula. Okay, the initial phase is pi over m. Yeah, it's pi over m. Yeah, m is the level. Yeah. So that's why this is the initial phase, because 0, 0 is start from the initial phase. So the theta here should be pi over m. So it's 1, 2, 3, 4. You get 4 level. So initial 1 should be pi over 4. So which is pi over 4 here. So it seems like it's easy to understand, right? Based on the constellations diagram. Getting some questions? Oh, okay. Yin, you get any questions? Getting a question mark here. Okay, you can ask me later on. Yeah, you can type it. Okay. So now we go to 0, 1. Yeah, 0, 1. So 0, 1 is here, right? So just need to. So what is a theta? So what's gonna be the theta then? Let me use a different colors. So what is the angle here? Yeah, in between. So what you're gonna do is, because this is the right angle, right? So the theta plus the right angle, which is pi over 4. That's right, not pi over 4. It's a pi over 2, yeah? And that's it. That's become the angles. But you can see, because this is the PSK scheme, so the amplitude is gonna be the same, which is a pi 2 square 2, yeah? Square root 2. So that's gonna be 1 over 4 pi plus 1 over 2 pi, yeah? that's equal to 3 over 4 pi. So this is where these numbers come from. Yeah. Then we go to another one. Yeah. Oops. We go to 1, 1. Yeah. So 1, 1, the amplitude is the same. Yeah. But the thing is, how about the degrees? Yeah. The degrees. I use another one. Yeah. So what about this one? Yeah. So again, you can see this is a theta, a plus. You can see this is a pi. Yeah. It's a huge angle here. It's a pi completely. So you just need to get the theta plus pi, which is pi over 4 plus pi. Yeah. So you can see this is pi over 4 plus pi. So it's equal to 5 over 4 pi. So 5 over 4 pi, you can use the 5 over 4 pi here to replace it, or you can completely reverse it, become a negative side, which is equal to minus 3 over 4 pi. So how to convert it? I leave it to you because this is high school mathematics. Yeah, I will not explain this one in detail. Yeah. Okay, then for 1, 0, which is the last one. 1, 0, yeah. So 1, 0 for the last one. Again, you can see a magnitude is the same, no change. And then the angle is all the way, yeah, all the way from here to here. Wow, it's a big, isn't it? So what you're gonna do is, yeah, what we're gonna do. It's not difficult at all, right? So what we're gonna do is you get in a 2 pi minus this angle, and that's all, yeah, because they all equal together, yeah. So it ends up to be getting this one plus 1 over 2 pi, or just getting a 2 pi minus you're getting getting a just wait, let me go back. You're getting a so you're getting 2 over pi over 2, pi over 2, pi over 2, and plus this angle that's become the whole lot here. So you can I trust you guys gonna calculate it without any problem. Or you can just go to, you're getting this angle already, right? So from here to here is a right angle, right? So you just need to, this angle we already calculate just now, yeah? And plus pi over 2, which is a right angle, and become the whole angle like that, yeah. So that's gonna be minus 3 pi over 4 plus pi over 2, which is a right angle, and equal to minus pi over 4. So this is where the angles can calculate it from. I think people get a question, yeah? 0, 1 is in, yeah, something like that, yes. Can answer 1, 1, yeah. I think, in my opinion, it should be okay. If your answer 1, 1 is become 5 pi over 4, yeah, without any problem. But you can better convert it to a -1 maybe, because that's the solutions. But for me, if I'm the exam marker, I will give you a full mark without any problem. Yeah. So for Hong Yin, how to set the 1, 0, 1, 1, 0, 1, 0, 0, it's given in the answers. It's given in the answer already. So it's given in the question. Sorry about that. It's given in the question. So in the question, you already given by the question here. Yeah. So it's given by a question. You can swap it without any problem, but this is a questions. Yeah. So I'm not make it a 0, 0, 1, 1 myself. Yeah. It's all given in the questions. Such as 0, 0 is no, if no give. Well, I think it's very conventional. It's a very conventional constellation diagram, I think. I recommend you to look back to the textbook to have looked what's the conventional way, but I think it's very conventional like that. But different bit combination, they can have different magnitude, magnitude, the in plane or the contrary, the quadrature. So I think in the question it should be given. Okay, seems like Hong Yin is typing the questions. Okay, so how about I go through the next one, and then can keep a much more efficient. Yeah. So for the second one, so which is you can break it into 101, 101, 001, and 010 because it's an APSK. Because APSK, you get in a 3 bits, same for each time. Yeah. So that's why the data sequencing can break into each 3. You can see 101 and 101, the first combination and second combination are the same. So we can just use 101 here, yeah, and 001 and 010. So that's why I get these three combinations here. Okay, so now we're gonna try to calculate, yeah, see what's going on. So let's go for we can go for 101, see which one easier, yeah. Okay. So this is my screenshot, yeah. So 101, yeah, 101 is here. Okay, 101 is here, yeah. 101 here. It looks like, the how can I say, this one is not perfect circle, isn't it? So maybe its drawing is not so perfect. But what we can do, is, you can see something here, right? So this is a circle, yeah. So what we can do is the magnitude here is just the radius. So you can see the circle is almost, yeah, something like that, right? Yeah. So this is a circle. So the radius is 1. Yeah, the radius is 1. And the radius is 1 here, yeah? So that's why the magnitude should be 1, no matter which dot it is, because it's an APSK, yeah? So that's why you can see the magnitude here is all 1, yeah? It's all 1. Okay, so for 101, we have to calculate the angle, yeah? The angle here. We have to calculate the angle. So remember, the initial phase, let's look at the initial phase is equal to pi over m, yeah? So now we get in a APSK. So that means the initial phase is pi over 8, yeah? It's pi over 8. Yeah. So that's why, 101, it can be the whole lots, yeah? The whole, which is pi over 2 times 3, so it's 3 pi over 2 minus the pi over 8. So it becomes the angle like that. So it just, it seems like a high school math, isn't it? Yeah. And actually here I can make it, a bit, details here. Yeah, this is my solutions. So you add up each together. Yeah, you add up each together, so it become 11 over 8 pi. You can put the 11 pi over 8 here, but I think you better change the negative side. Yeah, the negative side. So which is equal to minus 5 over 8 pi. Yeah, so this is easier. Yeah. So how to convert from 11 over 8 pi to minus 5 over 8 pi? Now, this is a high school things, and I expect you guys can do it, yeah, without any problem. Okay, so for 001, 001 is here, yeah? So let me use another colors. Yeah, 001 is here. Yeah. So you just need to calculate the angle because the magnitude is 1 without any problem. Yeah, it's 1. So you just need to calculate these angles. Yeah. So how to calculate these angles? So this is my calculations. So it's 1 over 8 pi plus 1 over 4 pi. So my logic is, because this is the initial phase here, yeah, it's 1 over pi or 1 pi over 8. Then the angle between each other here is pi over 4. So that's why it's 1 pi over 8 plus pi over 4. Or what you can do is something simple, right? You can see the angle here, yeah, from this one, from the previous 101 angle, right? You can see this is a pi, yeah, the pi from here to here, yeah, I use a different color. Yeah, this is pi. So what I can do is I can use the angle for the 101 minus pi and should be equal to the angle for 001. Yeah, so it's the same. I think it's the same, right? So what you can do is I just do some calculations. So what it is 11 minus 11 over 8 pi minus pi. So 11 over 8 pi minus pi, which is a over 8, right? So it becomes 3 over 8 pi. Yeah, so it's the same. It's the same answers. So you can see the constellations diagram give you a very flexible calculations. Every approach, can work. What you can do is just need to, you just need to say, okay, I just need to calculate this angle, and how can I calculate it? That's all. Yeah. Then 010, yeah, 010, 010 is here, yeah. 010, yeah, it's here. So again, the magnitude is 1 because it's a circle. Yeah, even though it's not perfect, but you can do some approximations. Then you just need to calculate this angle, yeah. Yeah, this angle. Yeah, how this angle gonna be calculated? So what you're gonna do is you can say, okay, I know the angle for 001. Yeah, so I just need to add the 001 angle and plus this one, yeah, without any problem. Or the other one is I know the angle for 101. Yeah, I just need to minus the angle between here and to here, see which one is more flexible. So what my approach is, I just need to edit that. So what I can do is I get in this one. Oh, sorry, 000. Yeah, and adding the pi over 4 and pi over 4. Actually speaking, is the angle at 001 plus pi over 4. And so getting the angle for 010. So it's a high school math, yeah. So which is here, it's complete here. That means it's yeah. So we know about the 0013 angles, yeah. 3 pi and plus 1 over 4 pi. Yeah. So 3 over 8 pi plus 1 over 4 pi, which is a 2 over 8, yeah. So it's a 5 over 8. Yeah, so it's a set. So it's 5 over 8 pi. So you can see, once you draw something like that, that should solve the question very easy. Okay, so any questions for this? Yeah, so I hope you guys can at least draw the constellation diagram over there. You can use the pencil to write it, to draw the angles and eventually become, yeah, that's right, eventually become a simple mathematic calculations. Okay, so if no questions, or you can ask me any question after the solution, yeah? So yeah, this part is easy, good, okay. So now we go to the the final one, which is slightly a little bit difficult. Yeah. So when you go to 16 QAM, so getting 4 bit each time. Yeah. So that means you break it into 1011, 0100, and 1010. Yeah. Now, if you look at the solution, looks like Katrina is using a using a this is the implant, and this is the conjuncture. Yeah. So to get in a superpositions, getting superposition. But what we can do is we can use a constellation diagram to look at it. Yeah. So for the constellation diagram, I just screenshot something like that. Yeah. Okay. So now the first one is 1011. Yeah. So 1011 is here. Yeah. So that means we have to calculate the magnitudes and also calculate the angles here. Yeah. So for calculate the magnitude, because it's not PSK anymore. Yeah. So that's why we have to there's no initial phase anymore. So we cannot use a trick for the first and second subquestions. So let's go to the most simple one, which is the magnitude. Yeah. So we have to know this one, but now we know the magnitude from here to here is 3. Yeah. And the magnitude from here to here is 1, isn't it? Yeah, it's 1. I mean the absolute magnitude. Yeah, is 1. So so the magnitude from here to here is easy, yeah, because it's a trigonal calculations. So it's become 3 square plus 1 square. So it's a square roots. Sorry, it's 10. Yep. So that's why you can see the magnitudes. Yeah, the magnitude here is a square root 10. Now we have to calculate the angle. So we have we either have this one or this one. Yeah, it's the same. This angle here. Yeah, see which one is the best. Okay, so now what we can do is, if you guys still remember the high school math, so to calculate this theta angle, yeah, the theta angle from this one specifically, let me just use another color. This one. So we have to use a tangent formula, isn't it? Because you know about 3 and 1, yeah. So it's gonna be the tangent x. We call the theta, yeah, is a tangent x equal to 1/3. And then how to calculate the angle? You can use the calculator, yeah. You can go to arctangents, or tangent minus 1, yeah. Then you know about the angles. Yeah, I'm pretty sure you guys can use a calculator, isn't it? Yeah. So I doing the arctangents formulas in the calculators. So the degree, the angles here, yeah, is 18.43 degrees. Yeah, 18.43 degrees. So this one is 18.43 degrees. This one here. Then how about the whole angle completely? Yeah, so it's gonna be 360 degrees because it's a round, right? Minus 18.43 degrees, it becomes 341.57 degrees. Yeah, this is in degrees. Then it's equal to minus 18.43 degrees because this is the conversions. but this is in degrees, right? So you have to convert it back to the radius. So the radius is minus 18.43 divided by 180 times pi. And that's it. Sorry, minus 18.43 divided by 180 times pi is a radius. So this is how this one, it's come from. So how this one's come from. So anybody have any questions? It's a little bit simple, isn't it? Okay, so seems like okay, somebody's typing. Okay, so let's wait for the question. Oh, okay, seems like it's fine, isn't it? Okay, so let's go to the second calculations. Then the second one is 0, 1, 0, 0, yeah? 0, 1, 0, 0. So 0, 1, 0, 1, 0, 0. Oh, okay, here, right? Okay, I use another colors. Okay. So what we need to do is we have to calculate the magnitudes, yeah? And then we also calculate the angles. Yeah, the angles here, yeah? So now what we're gonna do is we follow up the same method that we used just now, yeah? So you can see from here to here is 3 again, it's 3. And from here to here is 1, yeah? So what is the value here? Square root 10 again? Yeah, square root 10 again. So that's why it's a square root 10 here showing. Then now is the angle. So again, use a tangent, right? Tangent. A tangent theta equal to 1 over 3. So you're doing the arctangent again, so it becomes 18.43 degrees. But this is in degrees, yeah? When you convert to radius, it's become 18.43 divided by 180 times pi. So this one is much simpler than this one because this one is you calculate the angle all the way through from the origin point. But for 0, 1, 0, 0, it's only this angle. So it's simple. You don't need to do any conversions. Okay, so our x is a degree, it's an angle, yeah? It's the angle here. I just using for x example, yeah? X is examples because I can't type theta in the Adobe Adobe readers. Yeah. Okay. Okay, I wait for you guys' questions. Maybe you guys type in, yeah? Okay, I have question. Okay, what we can do is I meant on. We can do it. We can do this one after I went through all the questions. After I go through all the questions. Yeah, it's fine. Yep. Okay. So now let's go to the 1010. Yeah, 1010. So 1010 is here. Yeah. I use these colors. Maybe it's better, isn't it? Okay, 1010. Then I have to know about the angles, yeah, all the way from here to here. Yeah. Okay. So now, again, we follow up. We have to calculate the magnitude first. Yeah, magnitude first. So you can see the magnitude from here to here is 1. Yeah. From here to here is 3 again. So what the magnitude for the 1010 is square root 10 again. Yeah. So you can see it's square root 10 here. Then what is the angle? So you can see that this whole angle is here, but something is not difficult. Yeah. So what we need to do is we need to go for this angle, theta, or yeah, theta here. Because this one is a right angle, right? It's a 90 degrees. Yeah. This one is a right angle. It's a 90 degrees as well, yeah. And this is a right angle as well. So it's all 90 degrees. So what you're gonna do is 90 plus 90 plus 90 and plus a theta is the angle. So how to do it? Yeah. How to do it? Just the tangent again. We use the tangents to make it simpler. Yeah. So that means it's 18.43 again plus 90 plus 90 plus 90, which is 270. Yeah. So become 288.43 degrees. And this one is equal to minus 71.57 degrees. Yeah. If you're doing the conversions. Yeah. Maybe Katrina make a mistake. 71.57. This is there's some rounded. Yeah. The dot. How many decimal? Yeah. At the back. So that's equal to this equal to minus 7.1 minus 71.57 divided by 180 times pi for the radius in the radius scale. So I get in 0.01 difference with Katrina's result, but I think gonna be okay because this regarding on your calculator, how accurate your calculator gonna be. You know how many decimal point you're gonna round it. That's all. So this is all it comes from. So you can see, all in all, you can just use the constellation diagram to calculate the magnitude and also the degrees. It's very straightforward. So you don't need to use superpositions here at all. Because superposition, you have to use quite complicated formulas. So I think the constellation diagram is much more simpler. Okay, so I think that's all for the tutorial questions. So you can see the first and second question about the bandwidth. Yeah, so you have to really comprehend the formula that listed in the pre-exam workshop lecture slides. And then for the final one, you have to make good use of the constellation diagram to try to understand. So magnitude, you using the triangular mathematics, yeah. And for the angle, you can sometimes have to using the initial phase, yeah, for the PSK technologies. And then you add it one by one. Everything is just like high school mathematics. You just make it when you lay down into the constellation diagram, it will make it much more easier. Okay. Part B. Okay. B. Okay. Let's answer one by one here. Yeah. So Man Hong, I'm gonna answer it later on. So Kin Chong for part B, does it observation to decide the radius of one? Yes, that's right. From the observation. So Kin Chong, yes, is the radius of one. Yeah. So that's why it's almost like a perfect cycle. So we can say the radius is almost equal to 1. Yep. So so your answer, I will say, is yes. And for Chung Hang, let's see. Quite a bit. Okay, so Chung Hang, so for QAM, right? So actually speaking, you don't need to worry about the 10 or 11 position at all because it's all depending on the questions. So what we have here is all about can see it's all given in the questions. It's all given in the question. You can actually, 0, 0, you can go for 1, 0, 0, 1, 1, 1, something like that. That's without any problem. So it's something that you define it in the constellation diagram. So normally speaking, the question will be given in the exam paper. Okay, yeah, you're right. Okay, so for him 1, how to calculate the angle of the part B. Okay, okay. So actually, Hoi Wan already explained it. Okay, so I know pi. Oh, okay, 1/4 pi. Yeah. So what it is okay. So this is actually this angles here is pi/4 already. Yeah, it's pi/4. This is because how can I say? Because this is like, for instance, the distance. Yeah, you can see the distance from here. This is double. You can see this angle, because each point to the boundary is pi/8. Yeah, so you're getting two parts here. So that's why the thing between here to here is pi/4. So this is where the pi/4 comes from. Yeah. So does it make sense, Kinhwa and Hoihwa? Yep. Okay. So let me answer Ben On's questions. So which related to tutorial 1, the problem let me just divide by 2. Okay, let's open the question first. Okay. The problem, DSB, SC, and when the signal was modulated, the amplitude should be divided by 2. It is because the graph was keeping the amplitudes. Okay, Manhorn, I assumed in, okay, divide by 2. Oh, okay, I know. So I'm pretty sure that you mean y is divided by 2, right? This is the Fourier transform. Yeah, this is the rule of the Fourier transform. It's not about, or is the graph keeping the same. It's regarding the calculations using the Fourier transform. Yeah, so this is the rule. So if you're not sure, you can actually you can go to Wikipedia to look for the Fourier transform operation rules. And I'm pretty sure also the textbook should explain very well. So this is the mathematical calculation. It's not because the graph saying something like that and should be something like that, right? So am I answer the questions? Okay. Okay, I mean, AI should be divided by 2. Okay, let me go back. AII. You mean the okay? Still can't catch the meaning. Oh, okay. Cannot this be modulated after? Okay. Okay, so now I think you might have some misunderstanding. Yeah, because here, right? So this is a carrier, right? So for DSP-SC, it should not show the carrier there because it's not it's because it's a waste of power for carrier. So the carrier will not show in the spectrum in the frequency spectrum, right? So what it show is actually speaking is the same amplitude from the one, yeah, from one, the same amplitude for one. You know, you can see this is 1, 0.5, 0.5, and 1. It's the same here. You know, you can see this is 1, 0.5, 0.5, 1, 0.5, 0.5. So it have nothing to do with the carrier amplitude at all here. It's not just say that divide by 2, because when you divide by 2 here is the Fourier transform calculations. Yeah, but for the number 2 here, there's no divide by 2 because this is we neglect the carriers in the DSP/SC modulation technologies. Yeah. Okay. Can you show the puppy diagram again? Oh, okay. Just wait. It's a bit messy, isn't it? Okay, so this is a diagram. Okay, I've stopped this one for a few seconds. Then I will answer another questions. Okay, so why? Let me see. Why? Okay. So y is 1 over p plus pi plus 1 over 4 pi. Oh, so you mean here, right? So, okay. So this is for 101. Okay, 101. So that's 101, yeah? Okay. So let me just do a, yeah, because it's a bit. Okay, 101. Okay, and it's two options, right? So in here, we say is 1 over 8 pi plus pi plus 1 over 4 pi, right? So what my meaning is, okay. Oh, okay. Let me make it a bit simpler. Okay. So what it is we know this angle here, yeah? This is the initial phase, right? This is the initial phase, which is pi over 8, yeah? So for 101 is all the way from here to here. So we know this one. Then if we know about this one, and from 001 to 101 is pi. Yeah, because you can see it's a straight line here. So it's a pi, yeah? And for this one, from 001 to 000, you can see what we can do is, you can see this angle. Yeah, and these angles are the same. Yeah, because they share the same magnitudes. And also the, I mean, because it's divided equally, right? So what it can do is, what about this angle is pi over 2 because this is a right angle, yeah? Pi over 2 minus pi over 8 so this one, and minus another pi over 8. Yep. So that become pi over 4. So it's this angle, yeah? So eventually, we just need to calculate this angle plus this angle and plus the angle here. And this angle here. So that is a pi over 8, which is this one. And this one is pi over 4. And plus, from here to here is pi. So this is where it comes from. Yes. Okay. Yeah, something like that. Yeah. Difference between of FW between FSK bandwidth in blue and square shapes polar analysis. Okay, that's just number 6, yeah? Number 6. Okay. So now this is the bandwidth of the FSK, isn't it? So this is the transmission bandwidth after modulations, and this is Cousin rules, right? Cousin rule, that means it's by definition is 98% possibility that is fall into the cousin rule bandwidth. Yeah, this is something that I already talked about it in the last question of the tutorial 1. So this is 1 plus beta. So beta is the modulation index, right? B. So B, for instance, this is if your baseband transmission signal is, for instance, is polar NRZ, yeah. So that means the bandwidth, it should be the bit rate, yeah. Should be bit rate. So now we just need to calculate the beta, which is the modulation index. So the modulation index here is the frequency derivation, which is delta F max. So equal to the frequency between bit 1 and bit 0 for the of the carrier, yeah, and divided by the B, which is the bandwidth of the baseband, yeah. So this is how it goes. So you substitute into it and doing some, calculations, yeah, delta F max divided by B become the beta here, yeah. So you cross over to each other, cancel it to each other, it's gonna become 2 times the delta F max plus 2 bit rates. So we can actually substitute this one into it without any problem. And for right cosines, because for right cosines, it should have the 1 plus R in front of the bit rate. This is already talked about it in the lecture 2, yeah. So this is actually how it goes. Okay. Okay, good. Win you puppy, because puppy is a bit yeah, become a bit ugly already. So yeah, this is how the diagram looks like. Yeah, I just call it here, yeah. Okay, good. Oh yeah, that's right. So you are for the polar NRZ, right, the bit rate equal to the bandwidth is shown in the lecture slide yesterday. Yeah. So it's gonna be in I think in a table, right? Remember, it's a table. So please look at it already. Yes.